Welcome back to Linear Algebra Done Right by Sheldon Exler. So we're continuing the exercises in section 3D today. So I guess we start with question 5. I think that's where we last left off. So given range T1 is equal to range T2, I want to show that exists S such that T1 is equal to ST2. Okay. So here's the thing, right? Consider this, that for, let's see. So T1 and T2 have the same range, it's just that S might take the benefit of shifting some of the inputs to where it makes more sense. And let me just briefly think about what that would entail. So if something is like V is in the null space of T1, that must also be in the null space of T2. And the reason is because then T1 of V will be 0, and since S is injective, then T2 has to evaluate that thing to 0. Otherwise, if T2 of V is something non-zero, then S of something non-zero is not 0 by S is invertible and thus injective. So then you can say that the null space of T1 is within the null space of T2. In a similar manner, you can say null space T2 is within the null space of T1, so therefore null space of T2 is the null space of T1. These two have the same null spaces. And of course, because they have the same null spaces, you can establish a basis for it, and everything which is not in that basis will be what makes T1 and T2 not 0, right? So then once you extend that basis, everything that's in the basis of V but not in the basis of the null space of T1 will be what we want to examine, because that's where the interesting stuff happens, right? But then thinking about it that way, what you're gonna do is, let's say, so V subtract or not quotient, you don't want to do, well, maybe quotient is another way of describing it, but these two are the same, right? And this is entirely spanned by the basis of V minus the basis of the null space of T1, and the same over here. So then what you have here is really everything that produces some value is in the same place inside V. Oh wait, I screwed this up. This T2 composes S, not the other way around. Yeah, okay, so none of this holds. This is all incorrect. Okay, I have to resync this. Okay, so first we'll establish a basis of V and call it V1 through Vn. And then let's think about a definition for S, right? Because that's usually how you want to go. You want to define S. You want to show it's an invertible linear map. And then you want to show that T1 is T2 composed with S. But that usually follows from the definition of S. T1 is T2 composed with S, that is. So if you have T1 is T1 of some arbitrary V is equal to W, then you want T2 composed with S of that V to also be W. let's say since range of T1 is equal to range of T2, there must exist V1 such that T2 of V1 is equal to W. So this is the same W. And then considering this, we'll just SV is equal to V1 by such a definition, right? And this indeed defines every single V. This defines S for every single V inside the set V. We can go through this process of definition. That's quite fine. It's a bit convoluted, but I think it works, right? And for such arbitrary V, T1 of V is going to be equal to T2 of S of V. So it's just going to work out. But the thing now remains to do is to show that B is indeed invertible. And in the context of this, then you want to show invertibility from injectivity and surjectivity, right? So that might be a bit complicated. So let's say that S of V1 equals to S of V2 is equal to some W, but V1 is not equal to V2. Right, that means T2 of V1 is equal to T2 of V2 is equal to some W. But that means T1 of V1 minus V2 is equal to W, and then V1 minus V2 is in the kernel of T2, I guess. But yeah, here we want to talk about non-zero W's, so this shouldn't happen. Oh, sorry. Yeah, okay, no. Yeah, I think the other way around is actually much easier. If you have T1 is equal to T2S, then to show the range is much easier, because then you can just say like, if there exists something inside the range T1 but does not exist in T2, the range of T2, then let's say since it is in the range of T1, then there exists V such that T1 of V is equal to W. And then let's say then T2S of V is equal to T2 of V1 is equal to W, but V1 and V. So in fact, W was inside the range of T2 this whole time. So there does not exist a W in range T1 which is not in range T2. Therefore, range T1 is a subset of range T2. And you want to do it the other way around. So if you have range T2, so if you have some arbitrary W inside range T2 and is not inside range T1, let's see how you proceed from here. So ideally we would like to do a double containment, but that's not always guaranteed. So there must exist some V such that T2V is equal to W. There also must exist some V1 such that S of V1 is equal to V by S is invertible, and operator over finite dimensional space. So if it's an invertible and an operator over a finite dimensional space, that means that S is surjective, which means that you can find this. And then what that means is T2 composes S of V1 is going to be equal to W. That doesn't make sense because W1 also has to be equal to W, yet W1 is inside B. So W is inside the range of T1. So this means, in fact, that range of T1 is the same as the range of T2. Another way to think about it is that S doesn't really compress anything. So S is just moving different elements around. What you already have in the range, it's not going to ruin it, right? S is just moving the inputs around, it's shuffling the inputs around. So what was going to be the output of T2 is still going to be the output of T2, just maybe for a different input. So nothing really changes, right? But then we want to go from this side and say that if range of T1 is equal to range of T2, then exists the operator S, so that T1 is equal to T2 composed with S. This one's probably a little bit more difficult, I think. Let's say for arbitrary V, T1 of V is equal to W. Or no, perhaps we don't want to do it this way. We already tried this way. We want to use a linear combination in terms of its basis. Geez, I'm gonna fall asleep at the screen. Ugh. Yeah, maybe I should put on some music. Maybe that will help. How about just some basic Finnish meme music? That's probably what this is most appropriately called. Yeah, there we go. We now have some Finnish meme music. Yeah. Oh, it's not really a meme if it's uses the context of a war, but use it to blow up Russian mines, and I consider it to be kind of a meme. Yeah, man. That construction of S I already got down. So for arbitrary V, what you want to do is first you get TV is equal to W, and then you got T2 V1 is equal to W for some V1, and then also V is equal to 1 for some V, right? Now that jump, right? This is what you want to do. But how do you show that S is actually invertible? The easiest way to either show it's injective or surjective because S is an operator, and that's good enough. Right? So let's say that indeed there were, let's say the kernel is not 0, right? S of V is equal to 0 for some V which is not 0. And T2 composed of S of some V is equal to 0. But previously I think we showed that kernel of T1 is equal to the kernel of T2. So this is not in, oh, hold on. Well, what if V is in the kernel of T2? And that's not good. Yeah, no, I can't play tricks here. I gotta think of something actually genuinely interesting or useful. Can't play tricks with quantifiers and screw around. Maybe I should define S differently, because while this definition probably works, it doesn't work well trying to prove it's invertible, right? So let's say form bases of range T1 is W1 through WK, for example. Then what you got is T1 W1 equals W1. And then Wi exists for all I. Yeah, this is true, right? Then what you probably want to show from here is you somehow say the same thing for T2, right? T2 of Vi1 is equal to. And then what you do is a trick. S of V1 is equal to Vi1. S of V2 is equal to V2, etc. Something like this. You gotta do it. You gotta do a basis. Just makes things more secure. Yeah. I think then what you must want to show is in fact Vi1 through Vik are linearly independent somehow. Because if they're not linearly independent, then you perform a T2 transformation on the linear combination, which makes them not linearly independent. What you end up with, this is 0. And what you end up with is the linear combination of the W's are not linearly independent, so then you end up with a non-trivial linear combination of W's, which shows that the W's are not linearly independent. That's impossible because the W's in fact form a basis of range T1. So what that means is the VI's are all linearly independent in the first place, right? So if the VI's are all linearly independent in the first place, then to map from, let's say, a spanning set of V1, then to map from a linearly independent set Vi1 through Vik to W1 through Wk. Oh wait, sorry, no, that's not what you want to do. No, but you also indeed could show that V1 through Vk are all linearly independent in a similar way. Mapping from V1 to Vk in a linearly independent set to Vi1 through Vik. This is all completely injective because you're mapping from the elements of one basis to another, where the two bases have the same size. So this is completely injective, which means in fact that S is an injective operator. But then you can extend V1 through Vk as well as Vi1 through Vik into a full basis of V and map the rest of the elements of the basis accordingly. And then S is a completely injective operator. And T2 composed with S also exactly gives you what you would like, I think. Because let T1 be equal to T1 CV1, etc. CK, VK. But T2 composed with SV, so the inside is going to give you C1 VI1 plus CK VIK. And the result on both sides is just going to be C1 W1, C2 W2, CK WK. So that means the two functions are indeed equal. But I think this is actually like a not very great way to demonstrate such a thing. So there's definitely a better way to do this. So I'm just going to look it up. Because even though I've done it, it's not very elegant, and there's something definitely better, right? We go to chapter 3. Wait, this usually works. Go to chapter 3. I've used this website for a while. I don't think it's actually an official solution set, but whoever wrote it seems to have some basic knowledge of linear algebra, so they're not a fool, at least. They're probably better than what I know, at least. Let's just put it like that. Oh. Wait, no, that's matrices. I'm already past matrices. Durable and isomorphic. Okay, yeah, no, their proof was, that seems even more convoluted than what I had. So I'm not even gonna go there, because what they have seems probably just about as bad as yeah. So let's just say that's not an easy question, and the fact that I tried to think about it while doing this was kind of like walking on the street or whatever is probably not the best idea. I should just sit down and think about this more seriously. Well, yeah. Okay. Let's go question 6. Suppose V and W are finite dimensional and T1, T2 lie inside of the linear map from T1, T2. Yep. You want to prove there exist invertible operators S and R such that T1 to STR if and only if. Okay, so we'll go this way. If T1 is equal to STR2, T2R. And then we'll say that dimension of their null spaces are the same. So first we notice one thing, that these two must have the same null spaces. Then you just gotta figure out how to transform this into that somehow. Doesn't seem easy. But notice how they said R is invertible. So earlier I think what I did is I actually did write this down. I thought about this quite seriously. Then you can write it like, or S is invertible rather. Actually both are, but it does not matter in that way. So you get this, right? So kernel of S inverse T1 is the same as the kernel of T2R. But you know, since S and R are invertible and are linear operators, in fact, these guys have kernel of dimension 0. Right? And so does this. So does this R also has kernel dimension 0. Alright, so I'm starting to get the feeling that this S inverse and this R really don't matter in the grand scheme of the kernel. They don't really change the dimension. Like, they shift the kernel around for the composition, right? They don't really change the size of the kernel. Maybe to concretize that statement, there's something we can do. There's definitely something we can do. Fudge. So I want to say that the dimension of the kernel of S inverse T1 is just the dimension of kernel of T1. Because for all the members which were already in the kernel of T1, they are also members of the kernel of S inverse T1. Because S inverse is a linear map that takes 0 to 0. But for all the elements which are not inside the kernel of T1, they also are not inside the kernel of S inverse T1, because they will generate some non-zero value under T1, which S inverse cannot generate a 0 value of, because S inverse is an invertible linear map, which means it's injective, so it can't have a non-zero kernel. So in fact, the kernel of S inverse T1 is the same as the kernel of T1, and that's fine. I don't think it's something true with T2R and T2, because R can shift the inputs around. The kernel is not equal. But I think what could happen is, think about something like this. I think there was an inequality like this somewhere previously in the chapter. And notice kernel of R has dimension 0. So then that just means like dimension kernel T2R is less than equal to kernel dimension 2. And it should be equal to the dimension of kernel 2 for the fact that if you were to establish a basis of the kernel T2 composed with R, let's say you got some values v1 0 vk, or sorry, maybe I should just establish a kernel of T2 v1 0 vk. Then what will happen is there exists v r1 through vrk such that R of R1 equals to V1. R of Ri equals to Vi for all I, between 1 and k, let's say. And then it remains to show that VR1 and VRK are in fact linearly independent. Which is the tough part, but V1 through VK is a linearly independent set. So if VR1 and VRK maps to V1 through VK, then VR1 through VRK must also be linearly independent, because you need at least a vector space of dimension k to map to another vector space of dimension k. But if you even ignore that fact, if there's a linear combination that adds the R1 to RKs to 0, there will also be one that adds the V1 to VKs to 0. I guess transformation preserves linear combinations like that. So in fact, VR1 through VRK must be linearly independent. And if they are in fact linearly independent, then that means the dimension of the kernel of T2 is the same as the dimension of a kernel of T2 composed of this R. And then what that means is that since dimension kernel T1 is equal to dimension of kernel T2 composed with R is equal to the dimension of kernel T2, then the dimension of kernel of T1 is in fact equal to the dimension of the kernel of T2. And that concludes the first half of the proof. And in fact, you want to go the other way. You want to go the other way around as well. Otherwise, it's not the whole problem, right? You want to go the other way, right? So let's say dimension of null space of T1 is equal to dimension of space of T2. But in fact, they might have different bases that lead to such a null space, right? So how do you adjust the bases in such a way that these two are now having the same values using composition of linear maps? And I think one way to think about it is that if you have T1 is equal to ST2R, you probably want to do all the work in R, and you don't want to do any of the work in S. In fact, S should probably be the identity function. And then R is where you want to map the I1 to V1 and RVI2 to V2 and so on. I think that's sufficient. The identity map is of course invertible because the inverse is itself. And then this one is more tricky, but you can also show it because of course these two things, since this is linearly independent and so is this, you're mapping from a linearly independent space of size k to another linearly independent space of size k. And it's surjective mapping, so it must be injective, which means it must be bijective and thus invertible. So in fact, you construct S and R invertible such that T1 equals to T2R quite easily. By easy, I mean no insult. It's not easy, but like perhaps easier than the first half of the proof. Suppose we end up VR finite dimensional. Let V is inside some vector space V. Then you have this is true. Yeah, this is obviously a subspace. Okay, I keep saying obviously. I should not. I'm sorry. So let's take arbitrary elements S and T of such a subspace E. Then S of V is 0, and T of V is 0, and S plus T of V. You distribute by linearity of linear maps. Because linear maps also, don't forget, form a vector space, so you can distribute them quite well that way. And then you get 0, right? No, that's fine. That means S plus T is also a member of E. So the addition closure is fine. Then multiplied by a constant closure. So we want to say C times T of V is also a member of E somehow, but by linearity. This is once again true This is probably not called linearity, it's called homogeneity or something. This is also true. So indeed D is a subspace because it fulfills the addition and homogeneity requirements for closure. Of course 0 works because, you know, the annihilator, any annihilator belongs, well, wait, annihilator is bring it to the, no, this is not a dual space or whatever, because you're mapping to W, which is not guaranteed to be one-dimensional, but of course, this is definitely inside of V. That's not even a question. I think. And then going on the next one, suppose V is not 0, then what is dimension of V? This I thought about, and once it occurred, it became pretty obvious, but before that, it was a bit weird. So the dimension of the space of linear transformations from V to W, since V to W are finite dimensional, is just dimension of W times dimension of V. But since so V which is not 0 is mapped to 0 by such linear transformations. So let's say we start with this V, and then we construct a basis of the vector space V by expanding it into the full basis of V. Now let's say V has dimension n, then once you expand into the full basis, what you'll get is V through Vn minus 1. And then what you will get is you want to map this and this element alone into 0, while the other elements are free to map to whatever they want. So you can generate some linear combination of elements in W, or a basis of W for such an effect, right? Oh, sorry, this would be an M. Yeah, this would be an M. So, sorry, this would be M minus 1. So you're starting to see like the matrix take shape where really one entire column is just zeros, and this is the first column, and the other columns have non-zero coefficients, and it's a big fat 0. So the dimension is in fact m minus 1 times m, or if you want to not use n, that's fine too. You got this. Yeah, I think that's what it is. Of course, maybe like if you would like to be more formal, you wouldn't like to use this kind of shenanigans, you can use the rank nullity theorem, and that's just fine, I think. Because let's say that can you use the rank nullity theorem? Maybe not. Oh, whatever, I'm too lazy. I think the solution's already reasonable. And I'm here to get the big ideas, not to obsess over details. I don't have the time for that. So you have a linear map from V to W which is surjective. And prove there's a subspace U of V such that T of U is an isomorphism from U onto W. Okay, so we got V mapping to W and it's surjective. And you contract, or you restrict the linear transformation, which is surjective, into a smaller subspace of V. Right? Everything else is extra anyways. And I think this looks perfectly reasonable to start off. But perhaps it's not so easy to find such a subspace. One of my first thoughts is that, well, form a basis of W, W1 through Wm, because everything is finite dimensional, right? And then, of course, there exists V1 through Vm, such that T of Vi is equal to Wi, because this is the range, right? Because since W is entirely inside the range of T, since T is surjective, so this must be possible. And once you establish something like this, then let's just say put the span of this as your new subspace, and then you're done, right? Then you're good. There's nothing else to do. Oh wait, also you gotta show it's an isomorphism, I forgot. So we want to show it's an invertible linear map. So you probably want to show that this indeed has dimension m, which you can, I think, because if it has less than dimension m, it can map to something of dimension m. And it can have greater than dimension m because there's only m elements in it. So it in fact only has m elements and they are all linearly independent. Which means once again you are mapping from this to this. And the kernel of such a map T is 0. Because if there was a non-zero kernel, then that implies some linear combination of this. Mapped by T goes to 0. That means some linear combination of W is 0. That just cannot be true for not trivial linear combinations of W's just because W's are basis, right? So then obviously, I keep saying obvious. So then you know that such a map T is injective. Injective T means the dimension of the kernel is 0, and since the range is dimension m and the input space is dimension m, then by the rank nullity theorem you know that the dimension of the range is m, which means it's both surjective and injective, which means it's bijective, which means T is in fact isomorphic. So, well, that's probably what you can say in the case of an operator, at least. Yeah. Well, okay, yeah, no. They are isomorphic, but we're not sure if T is the isomorphism that brings out that isomorphicness. And indeed, we don't know that injectivity is equivalent to surjectivity. We don't know that bijectivity is equivalent to invertibility because of the sheer fact that the range of T and U are not T is not an operator. But to invert it, I think wouldn't be a difficult task. Because then you would just say T1 brings W1 to V1 and so on. You can bring out such an inverse, right? Then it becomes irrefutable once you bring out the inverse. Linear combinations, because anything inside this U and inside this range of T must appear as a linear combination of W's and V's. And once you map each W to each V, the invertibility of it becomes a lot clearer. So something like this, let's say, becomes a lot clearer. Right, because this is supposed to map it back to C1, V1, and then these two are equal. And same as the right-handed inverse is not much different from the left-handed inverse. I think that demonstration goes pretty much similarly. Yeah, once again, this section is proving to be a very tough section. I don't think it's a trivial section. Yeah, I think the Zakiev and Foka is keeping me alive right now. Let's say V is finite dimensional, and S and T both lie inside the set of linear operators. ST is invertible if and only if S and T are both invertible. Okay, so we'll go from one side and then we'll go from the other. So ST is invertible implies that, well, what does that imply? I'm not sure. Let me pull out my notebook. I might need to do something. That might be a use. Oh no, currently I stopped writing here. Okay, so I don't have anything. Well, I mean, I was up to question 10 or 11 solving things in my head, but it's easy to forget if you don't write things down. Okay, that's quite enough of the polka. Yeah, maybe I'll just pause here. Take pause here.